Hello, in this video I'll be working through problems from the Unit 1 review. For question 1, we want to find the limit as x approaches 0. If we try direct substitution, we're going to end up with 0 over 0, and 0 over 0 is an indeterminate form that doesn't tell us anything. So algebraically, we want to simplify 2x to the 6th plus 6x cubed over 4x to the 5th plus 3x cubed, and then try finding the limit by substitution. One thing I can do is factor out an x cubed. So then this becomes the limit as x approaches 0. If I factor an x cubed from the numerator, I'm left with 2x cubed plus 6. If I factor x cubed from the denominator, I am left with 4x squared plus 3. And now I can cancel the x cubed from the numerator and denominator and try substitution again. So this time, when I substitute 0 in for x, I'm left with 6 over 3, which simplifies to 2. So my limit is equal to 2. Number 2, find the limit as x approaches 2 from the left of 3 minus 2x over x minus 2. If I use substitution, 3 minus 2 times 2 is negative 1. And in the denominator, 2 minus 2 is 0. We have a non-zero number divided by 0. So I know this is going to approach either infinity or negative infinity. Now we're approaching 2 from the left-hand side. As I approach negative 1 from either direction, the value of my number is negative. But as I approach 0 from either direction, I'm going to get opposite signs. Numbers to the left of 0 are negative, numbers to the right of 0 are positive. So I have to figure out, if I'm approaching 2 from the left, is the denominator approaching 0 from the left or from the right? So 2 from the left would be numerically something close to 1.999999999. And substitution in that case is going to give me, in my denominator, 1.99999 minus 2 is a negative number. So even though I'm writing 0, I know that it's not actually equal to 0 because we're just approaching 2. X doesn't equal 2. And so my denominator is approaching 0, but it's a negative number. So I have a negative numerator and a negative denominator. When you divide a negative by a negative, you get a positive. So our limit here is positive infinity. We can also say that our limit does not exist. Number 3, f of x equals 3x squared plus 2x, and we want to find the limit as h approaches 0 of f of x plus h minus f of x over h. So this is going to be the limit as h approaches 0. For f of x plus h, I'm going to go to function f and use x plus h as my input. So the x's here get replaced with x plus h's. So f of x plus h is going to be 3 times x plus h squared plus 2 times x plus h. Now I need to subtract f of x, and f of x is just 3x squared plus 2x. All of that over h. So substitution at this point is going to have us dividing by 0. So we're going to simplify this algebraically. X plus h, that quantity squared, is x squared plus 2xh plus h squared. Then I'll distribute the 2 in the next part. So it's 2x plus 2h. Then I'm going to distribute the negative sign in this last part. So minus 3x squared minus 2x, all of that over h. Let me go ahead and distribute that 3. So 3x squared plus 6xh plus 3h squared plus 2x plus 2h minus 3x squared minus 2x all over h. So we can eliminate our 3x squared minus 3x squared. That goes to 0. And then we have 2x minus 2x. That is also 0. From the terms that are left, I can factor out an h in the numerator. leaving me with 6x plus 3h plus 2, and still an h in the denominator. Then I can cancel out my h's, and now I want the limit as h approaches 0 of 6x plus 3h plus 2, and I'm going to find that limit using substitution. So when I substitute 0 in for h, I get 6x plus 2. Number 4, for what value of k is f of x continuous at x equals 2? Well, we have a three-part definition of continuity. So I know that if f is continuous at x equals 2, that means that f of 2 will equal the limit of f as x approaches 2. So f of 2, we're going to use this piece of our piecewise function for x equals 2, and then substitution, I'm going to get 2 squared, or 4, minus 3 times 2, so minus 6, plus 9. So that is 7. That's my f of 2. Now to find the limit of f as x approaches 2, I need to find both the left and right hand limits. So the limit as x approaches 2 from the left-hand side. From the left-hand side, we're approaching 2 from the left, so numbers smaller than 2. So again, we're in this top piece, and we'll find that limit using substitution, so we're just going to get 7 again. The limit as we approach 2 from the right-hand side, that means bigger than 2, so now we're in the bottom piece. And substitution, if we substitute 2 in for x, we get 2k plus 1. So in order for this function f to be continuous at x equals 2, I know that 7 must equal 2k plus 1. Subtracting 1 on both sides, we get 6 equals 2 times k. Dividing both sides by 2, we get k equals 3. So if k equals 3, then f of x is continuous at x equals 2. Number 5, f of x equals the quantity ax squared plus 12x divided by the quantity x squared plus b. We also have a graph of f of x, and I can see on the graph that we have a horizontal asymptote at y equals 2. I can also see that the function is approaching 2 as x approaches infinity, and the function is approaching 2 as x approaches negative infinity. So I know the limit as x approaches infinity of f of x equals 2. And if I take the limit as x approaches infinity of ax squared plus 12x over x squared plus b, so we know that that is going to equal 2. But if we didn't know that and I were taking the limit, I would get that this is equal to a. Using the shortcut, the numerator and denominator have the same degree, so I know my limit will be the ratio of those leading coefficients, a over 1 or just a. Or if we want to do this a little more mathematically, I can multiply the numerator and denominator by 1 over x squared. That's the highest power of x. And doing that would give me a plus 12 over x over 1 plus b over x squared. And that limit is just equal to a when we do substitution. So that limit has to equal a, and that limit also has to equal 2. Therefore, a equals 2. Now to find the value of b, we want to think about those vertical asymptotes. I can see on the graph I have vertical asymptotes at plus or minus 3. And that tells me that in my function, in the denominator, I must have a factor of x plus 3. That gives me the asymptote at x equals negative 3. And x minus 3. That gives me the vertical asymptote at x equals positive 3. We have ax squared plus 12x. And if we multiply that denominator out, that's going to be x squared minus 9. So by comparison, if my denominator is x squared plus b, if x squared plus b equals x squared minus 9, then b must equal negative 9. Number 6, we're given the graph of f of x and a number of statements, and we have to decide which of these statements are true, which of the statements are false. So statement 1 says the limit of f as x approaches 2 exists. And if we go to the graph, as we approach 2 from the left, our function is approaching 2. As we approach 2 from the right, our function is also approaching 2. So the limit is 2. So that's a true statement. Statement 2, the limit of f as x approaches 3 exists. So as x approaches 3 from the left, the function is approaching 5. As we approach 3 from the right, the function is approaching 5. So the limit does exist, it's equal to 5. So that is also true. Statement 3, the limit of f as x approaches 4 exists. Well, as we approach 4 from the left, the function is approaching 2. As we approach 4 from the right, the function is approaching 4. We're getting a different answer for our left-hand and right-hand limits. Therefore, the limit does not exist. That is a false statement. And statement 4, f is continuous at x equals 3. So here, f of 3 equals 5. F of 3 equals 5. And we already saw that the limit as we approach from the left and the right is equal to 5. F of 3 is equal to the limit of f as x approaches 3. Therefore, yes, it is continuous. That at x equals 3, that is a true statement. So 1, 2, and 4 are true. For number 7, we want to determine which of the following statements are reasons why g is not continuous at x equals 3. So statement 1 says g of 3 is undefined. Well, if we look at our piecewise function, when x is 3, g equals 3 root 2. So g of 3 equals 3 root 2, which is a real number, so our function is defined when x is 3. So number 1 is a false statement. That's definitely not the reason why this graph wouldn't be continuous at x equals 3. The next statement says the limit as x approaches 3 of g of x does not exist. Well, in order for the limit to exist, we need the limit as x approaches 3 from the left to equal the limit as x approaches 3 from the right. So let's find those limits and see if they are equal. As we approach 3 from the left, we're in the top piece, and using substitution, our limit would be the sine of 3 pi over 4. The sine of 3 pi over 4 is, we're in quadrant 2, so it would be positive 1 over root 2. The limit as we approach 3 from the right-hand side, I'm in the bottom piece, and substitution here would give me 3 root 2 over 4 times 3 is 12 minus 6 is 6. So that simplifies to square root of 2 over 2. Now 1 over root 2 and square root of 2 over 2 are actually the same number, right? If we rationalize this one here, we get square root of 2 over 2. So the left and right hand limits are equal to each other, and that means the limit as x approaches 3 of g does exist. So number 2 is a false statement. It's certainly not the reason why our function is not continuous. Statement 3 says the limit as x approaches 3 of g does not equal g of 3. Well, that's actually true because our limit is root 2 over 2, and g of 3 is 3 root 2, and those values are not equal to each other. And if that limit does not equal the value of the function at that x value, then the graph is not continuous. So statement 3 is the reason why this is not continuous at 3. Number 8, we want to know which of the following statements are guaranteed by the intermediate value theorem. So we're told f is continuous on the closed interval from 2 to 4, that f of 2 equals 10, and that f of 4 equals 20. So let's look at statement number 1. F of x equals 13. Well, f of x equals 13 is, 13 here is a y coordinate, and it is in between f of 2 and f of 4, the y coordinates at our endpoints. Since f is continuous and our value 13 falls in between f of 2 and f of 4, then the intermediate value theorem does indeed guarantee at least one solution on that open interval from 2 to 4. So this is true. Statement number 2 says f of 3 equals 15. Well, we don't know. It might equal 15, but we don't know that f of 3 equals 15. Just because 3 is halfway between 2 and 4 doesn't mean the corresponding y coordinate will be halfway between f of 2 and f of 4. So that's not necessarily true. It could be true, but not necessarily. Statement 3, f attains a maximum somewhere on the interval from 2 to 4. That's not guaranteed either. It could be that, so if we do a quick sketch here of our function, we've got f of 2 equals 10. Okay, so we'll call that 2 and 10. And then f of 4 equals 20. We'll call that 20. So it could be that f has a maximum. Maybe our graph does something like this, and there's a maximum. But it doesn't necessarily have to. Our graph could also do something like this and have a minimum. Or we could just have a straight shot from one endpoint to the other. So that is not guaranteed. Again, it could be true, but not necessarily so. And then statement 4, f of x has at least one 0 on the interval from 2 to 4. Again, that could be true if our function fell below the x-axis and then came back up, but we don't know that that is necessarily true since 0 is not between 10 and 20. The y-coordinate of 0 is not in between the y-coordinate at our endpoints, 10 and 20. So the intermediate value theorem doesn't guarantee that as a solution. So only statement 1 is guaranteed by the intermediate value theorem. Number 9, we're given a graph of function g and a piecewise defined function f. Part A, we're looking for the limit as x approaches 1 from the right of 2 times g minus f times cosine pi x. So using our property of limits, let's rewrite this as the limit as x approaches 1 from the right. Now, 2 times g of x, we can find the limit of g and then just multiply that by 2, like so. Minus, and then here, the next part is a product, so we can split this up and say it's the limit as x approaches 1 from the right of f of x times the limit as x approaches 1 from the right of cosine pi x, like so. The limit of g, so we're going to be looking at the graph, the limit of g as x approaches 1 from the right-hand side. So here our function is approaching a y value of 2. And then for the next part, we want the limit as we approach 1 from the right of f of x. So we're going to go down to our piecewise function. Numbers to the right of 1 are going to fall into this middle piece. So we're going to find that limit using substitution. When we substitute 1 in for x, we get 1 minus 3 or negative 2. Times, and now we want the limit of cosine pi x. So we'll just use substitution here. If we substitute 1 in for x, we get cosine of pi. The cosine of pi is negative 1. And then we simplify. 2 times 2 is 4 minus negative 2 times negative 1 is positive 2. 4 minus 2 is 2. Part B, you're asked to give one value of x where the function g is discontinuous. So you might say at x equals 1, and then use the three-part definition of continuity to explain why the graph is not continuous at that point. In order to be continuous, we need the limit as we approach 1 from the left to equal the limit as we approach 1 from the right to equal f of 1. Those three things all need to be equal. And we can see from the graph that the left-hand limit and the right-hand limit are not equal. The limit as we approach 1 from the left is 0, and the limit as we approach 1 from the right is 2, and those are not equal to each other. So the limit as x approaches 1 does not exist. Now you also may have, instead of x equals 1, you may have given x equals negative 7. The graph is not continuous at x equals negative 7 because g of negative 7 is undefined or does not exist. So the graph can't be continuous at a point where it's undefined. Part C, for what values a and b is f of x continuous everywhere? Well, if we look at the different pieces in our piecewise defined function, the first piece is linear, so that's continuous everywhere. The second piece is quadratic, that's continuous everywhere. And the third piece is linear, continuous everywhere. So the only possible places where we might have discontinuity would be where the domain splits, where x is -3 or where x is 2. So we're going to check for continuity at both of those x values. So we need f of -3 to equal the limit of f as x approaches 3. And in order for the limit as x approaches 3 to exist, we need the left-hand limit to equal the right-hand limit. So first of all, f of -3 equals, by substitution, we're looking at this middle piece because that's where we have equal to -3. So substitution is going to give us -3 squared, which is 9, minus 3 times -3, which would be 9 plus 9, or 18. The limit as we approach 3 from the left-hand side, for that, we're going to be using the top piece, and substitution of -3 in for x gives us -3a plus 3. So we know 18 has to equal -3a plus 3. The limit as we approach 3 from the right, we'll be using the bottom piece, so substitution would give us 18 there. Okay, so we have 18 equals -3a plus 3. That needs to be true in order for the graph to be continuous at -3. Now, in order for the graph to be continuous at 2, we need f of 2 to equal the limit of f as x approaches 2, again from the left and the right side. So f of 2, we're looking at this bottom piece, that's where x is equal to 2, and substitution, we're substituting 2 in for x, gives us 2b minus 5. And then our limit, as we approach 2 from the left-hand side, we're in this middle piece, and substituting 2 in for x is going to give us 4 minus 6, or -2. So we need 2b minus 5 to equal -2. The limit as x approaches 2 from the right will be in the bottom piece. Substitution again will give us 2b minus 5. So we need -2 to equal 2b minus 5. Now each of these equations only has a single variable, so we don't need to solve this as a system. We just need to solve each one of these equations. So for my first equation, if I subtract 3, I get 15 equals -3 times a, and if I divide both sides by -3, I get a equals -5. For my second equation, if I add 5 to both sides, I get 3 equals 2 times b. Divide both sides by 2, we get b equals 3/2. Number 10, we want the limit as x approaches pi over 2 of the function h times the quantity 2x minus 2. So we know from our properties of limits that we can split this up into the limit as x approaches pi over 2 of h of x times the limit as x approaches pi over 2 of 2x minus 2, which I could write as 2 times x minus 1, and then bring the 2 outside of my limit if we want to. So this would be 2 times the limit as x approaches pi over 2 of h of x times the limit as x approaches pi over 2 of x minus 1. Now you don't have to approach the problem this way, but let's see how this works out. Now using substitution, the limit of h as x approaches pi over 2 is going to be -2 times pi over 2, or just -pi, minus the sine of pi over 2, which is 1, over pi over 2 minus 1. Okay, and then we multiply that by this other limit, and using substitution, that's going to be pi over 2 minus 1. So right away we can cancel out pi over 2 minus 1 here and here, and then distribute our 2, we get negative 2 pi minus 2. Part B, identify any vertical asymptotes and justify their existence using a limit. So for a vertical asymptote, we want to see where our denominator is equal to 0. Our denominator is just x minus 1. So we set that equal to 0 and solve, we get x equals 1. Now we do need to check and make sure that the numerator is not also 0 when x is 1. If it is, then substitution there is giving us 0 over 0, and that's not going to be a vertical asymptote. That's going to be a removable discontinuity. So when x is 1, my numerator becomes negative 2 minus the sign of 1, which is not 0. So I know I have a vertical asymptote at x equals 1. And I can justify that using a limit statement. The limit as x approaches 1. Now I have to approach either from the left or from the right. It doesn't matter which one I choose. I'm just going to choose to approach from the right. So the limit of h of x as x approaches 1 from the right-hand side, we want to show that that's either infinity or negative infinity. So let's find that limit using substitution. If I substitute 1 in for x, in the numerator I get negative 2 minus the sign of 1. Over in the denominator, I get 0. But since I'm approaching 1 from the right, it's a number that's slightly bigger than 1. So when I subtract 1, that is a positive number. So the denominator, it's approaching 0 from the right-hand side. It's a positive value. The numerator is going to be negative. Even if you don't know what the sign of 1 is without looking at your calculator, we know it can't be less than negative 1. So the numerator is definitely going to be negative. We have a negative numerator, and we have a positive denominator, and a negative number divided by a positive number is a negative number. So this is approaching negative infinity. And make sure here when you're trying to justify vertical asymptotes that you don't just say does not exist. You must show that your limit as you approach some finite value is either equal to infinity or negative infinity. Now to find a horizontal asymptote, we're going to take the limit as x approaches infinity of h of x, and we're going to take the limit as x approaches negative infinity of h of x, because we want to determine the right end behavior and the left end behavior on the graph. So as x approaches infinity, well, I'm going to simplify my expression. So we want the limit as x approaches infinity, and to do that, I'm looking at h of x, and I'm going to divide everything by the highest power of x. So I am going to divide everything by x, or multiply by 1 over x over 1 over x. Okay, if I do that, this becomes negative 2 minus sine x over x over 1 minus 1 over x. And when I evaluate that limit, I'm going to get negative 2 minus 1, minus 0. The limit of sine x over x in this case is 0 because x is approaching infinity. If x were approaching 0, then that limit would equal 1. But since x is approaching infinity, that limit is 0 over 1 minus 0. Okay, so that limit is negative 2. If you take the limit of h as x approaches infinity and you get a finite value, then that shows the existence of a horizontal asymptote. So we have a horizontal asymptote at y equals negative 2. Let's check the other side because we may have a different horizontal asymptote on the left end of the graph. So here we want the limit as x approaches negative infinity, and I can reuse this same expression that I've simplified over 1 minus 1 over x. As x approaches negative infinity, this is going to give me negative infinity minus 0 still, over 1 minus 0 still, so also negative 2. So we have a horizontal asymptote at y equals negative 2. And part D, explain why the intermediate value theorem guarantees a value c on the open interval from 1.5 to 2.5 such that h of c equals negative 4. Then find the value of c. So we're going to use our calculator on this problem. First thing we need to know in order to use the intermediate value theorem is whether our function is continuous on the interval in question. So h of x, if we look at our equation up here, has a discontinuity when x equals 1. So there is a discontinuity at x equals 1, but that's the only place where we have a discontinuity. And since 1 is not in the interval between 1.5 and 2.5, we know that our graph is continuous on our interval. So we have h of x is continuous on the closed interval from 1.5 to 2.5, because we know it's continuous everywhere except for x equals 1. Now we also have to consider our endpoints. Okay, we need to know what is h of 1.5 and what is h of 2.5. Okay, so h of 1.5, and I'm just using my calculator to compute that, is approximately negative 7.995. h of 2.5 is approximately negative 3.732. Now our y value in question, the h of c value we're looking for, is negative 4, and that is in fact between negative 7.995 and negative 3.732. Okay, so I'm going to add that up here to the end of the statement I started to write. H of x is continuous on the closed interval 1.5 to 2.5, and h of 1.5 is less than negative 4, which is less than h of 2.5. Therefore, the IVT, the intermediate value theorem, guarantees that there exists a value c on the open interval from 1.5 to 2.5 such that h of c equals negative 4. Now to find the value of c, we want to set our equation equal to negative 4, but that's not something we're going to be able to solve by hand. So I have negative 2x minus sine x over x minus 1 equals negative 4. I'm going to graph both sides and my calculator find the point of intersection. And let me do a rough sketch. Right, left-hand side, our graph is coming in like so. Right-hand side, so this is negative 4. And we have a point of intersection here at approximately 2.354, comma negative 4. So our c value, approximately 2.354, and that is indeed in between our x values 1.5 and 2.5.